It's biology with Mr. B. Biology with Mr. B. That's me. Hi all. So what I'm doing in this video, I'm reviewing the questions that you guys have emailed to me about the exchange surface and breathing topic, in particular some fishy and insecty based questions as well that you forwarded my way, which I think were really, really cool. So hopefully, if you've sent me a question, I'm going to answer it. And if you haven't sent me a question, well, here's what other brains were thinking when they were doing those sort of questions that I set, when they were going through the fish and insect stuff as well. Okie doke. So, first thing to show you is, so on the, these are just the questions that I set. There was a couple more choices, and the first question that came up was actually calculating the surface area to volume ratio. So I'm not going to go through this majorly. You can see the mark scheme, the answer is B. But why is B correct? How do you actually go through a process of working out what that ratio would be of a cube? So all we know from B is that each side is worth 2 micrometers. I'm going to ignore the fact it's micrometers. I don't care about the unit. I care that the fact it is 2, which means every single side, every single square would be 4 centimeters squared. 2 times 2. Length times width. Therefore, because I know a cube has 6 sides, the surface area of the entire cube is 4 times 6, which is 24 centimeters squared. Volume is whatever the length or width is, whatever that number is, cubed. So in this case, it's 2 to the power of 3. 2 times 2 times 2, which is the same as 8 centimeters cubed. In terms of a ratio, it must be surface area to volume, which means it must be 24 to 8. How do I get both sides the same? Divide both sides by 8, and that would give me a ratio of 3 to 1. That's why I know B has a ratio of 3 to 1. Okie dokie. Next question that pops up was this one. Some of the questions raised by this question were about, they actually do with expiration, why is it passive, but also just generally the use of the term passive in context of the sort of bits of biology that we've done. So first, for this question, why do I know that expiration is a passive process? I know that because there is no muscular contraction whatsoever. And no muscle contraction, I know it's only one marker, no muscle contraction means I've not had to make any ATP. No metabolically produced, released energy. Shouldn't really be using the word produce, should I, when it comes to energy? But the key idea is, because there's no muscle contraction, there is nothing that your body is doing to actually produce more ATP or release more energy to make it happen. Yeah, of course there's energy involved to breathe out. Of course there is. But that energy isn't, there's no extra energy. You're not expending any extra energy by doing any respiration. So in particular for expiration, why can your lungs just suddenly change shape and your ribs go in? Well, it's because of those elastic fibres. Those elastic fibres within the bronchioles, alveoli as well, they are recoiling. And that recoil changes the shape. And therefore changes the volume, changes the pressure, and air goes out. In terms of the term, we've come across passive before in the idea of diffusion, and therefore obviously facilitate diffusion and osmosis. In that context, being passive just meant, of course there's energy involved. If things are moving, there must be energy, because there must be kinetic energy. But we can call it passive as long as there is no metabolic energy. In other words, you aren't having to respire to produce ATP for those molecules to move. So same for this question. Why is it a passive process? Because you aren't having to respire to produce ATP to contract any muscles, because there's no muscle contraction. If that said forced expiration, it would be an active process, because in forced expiration, that's when your internal intercostal muscles do contract, but only forced. So when you're exercising and when you're like going, yeah, okay, that was a bit weird. Anyway, keep going. Nothing on there. Yep, I had a request just to review these sort of longy graphs, which I think is always a really, really good idea to do. I'm just going to go through each letter where I can, but I'm going to start with the one that I always look for first. F. This line here, F, indicates someone who is breathing at a normal rate. So that volume of oxygen, that volume of air there from, okay, I can't exactly read what it is, but it's about 400 centimetre cubed worth from top to bottom. That is what is known as your tidal volume. And if you make someone breathe in as much as they can, and then follow that up with breathing out as much as they can, you are able to create C. So from top, this is the maximum inspiration volume, and this is their maximum expiration volume. From top to bottom, that is the vital capacity. They're the two big ones to look for. The other things you can look for is understanding that vital capacity is the addition of the tidal volume, the inspiratory reserve volume, which is basically how much you can inspire in addition to the tidal volume if you really tried, and the expiratory reserve volume, which is how much you can expire in addition to what you would at tidal volume if you really tried. So it gave you in the question that the inspiratory reserve volume was A, so the expiratory reserve volume in this case is from that line there to here, which is G. So G is the expiratory reserve volume. Other things within this, H, notice at no point is there any longer measurements for H. That is the air, in particular it's the volume of air, so just over 1,000 in this case, 1,250 centimetre cubed. That is the air that is remaining in the lungs after, even when you forcibly exhale. Remember, if there isn't air left in the lungs, the alveoli will just collapse in on themselves under the pressure change. So that H is your residual volume. Residual volume, the volume of air left in the lungs after a forced expiration. Other things I've not really mentioned, what is it, D? D is the entire thing. D is your entire lung volume. Because obviously when you have a maximum inspiration, you literally have that much, that volume of air inside your lungs at that point. So 5,500 centimetres cubed in this example. I think the only sort of letter I've not mentioned here is, I think, is it E and B? E is kind of an amalgamation. That is just everything, everything you can expire, plus residual volume. B, likewise, everything you can inspire after that tidal volume forcibly. Oh, plus tidal volume as well for B. So, hope that one helped. Either way, let's just keep it going. Okay. Now, most people, when they looked at the polymer question, they all said the same thing as, I didn't really get it, but then I looked back at my notes and I got it. Well done, guys. You've proven that revision actually works. Yeah, I can't stress this enough. Every single question that I've just given you, I literally picked it off from the 2016 and 2017 AS papers. So these are the actual questions on this topic from those two years worth of AS papers. These are the types of questions that they do. They give you something in context and they make you apply it to something different that you've learnt in biology. In this case, chitin. So you're there going, oh yeah, chitin, great insects. Oh yeah, tracheoles, well, great. But what they really want you to do is actually have your carbohydrate knowledge and link the two together. So yeah, if you've learned that looking back at your notes helps, fantastic. Please keep it up. Keep looking back. Designate a little time period in your little window of biology for the week where you just look back at a topic. Just look back at enzymes, looking back at cell order structure, just that little bit. Because every little bit you do is going to massively add up. Every 10-20 minutes here or there becomes 10-20 hours by next year and next summer, when presumably you will have exams. Unlucky. So, I was the question that threw people. So what do we actually want? Chitin, so using knowledge of the formation of structural polysaccharides, stop there. of the formation of structural polysaccharides. How do polysaccharides form? Well, you get two monomers together and you do a condensation reaction which produces water. Stop. I don't even need to read the question. I know that's going to be the answer, because that is how you make a polysaccharide. You take two monosaccharides and you put them together in a condensation reaction, making water to make a disaccharide. And you keep doing that again and again until poly just means many, so I guess 3 would count as a polysaccharide potentially. But now we got the rest of the question. Describe the formation of chitin molecule from its monomer and predicted structure. That, with the exception of the N group at the bottom here, that is an exact replica of beta glucose. And therefore you're going to get a formation which is virtually identical to cellulose. So we're going to also have the idea of alternating monomers are rotated 180 degrees. And that, like cellulose, is going to allow the molecule to be straight chained. Each of those were the marking points, but again you can see that on the bottom. But yeah, do keep looking back over other topics. Good revision. Okie dokie. So no more on that one. My final questions, I'm going to go back to my PowerPoint. See if I can get this a bit smaller for you. Okie doke. So first one actually talked about the countercurrent system. Again, this is a really, really good question. In the video I posted out the fish and insects, I sort of used my time to sort of draw a couple of arrows to show like if water's going this way, then in the gills the blood will be going the opposite way, a counter-current system. And the reason why that was so important was when it comes to oxygen levels, well, we know that the blood at this point here has, well, no oxygen left because it's all been used to respire in the tissues. And we also know that the water coming in, because it's not yet been to the fish, has as much oxygen as that water ever will have, so it's called 100%. So of course you're going to get diffusion of oxygen into the blood at that point, because it's 100% here, whatever's in the blood must be slightly lower. And then obviously there might be 80% here, but then 60%, as more and more oxygen gets taken in to the fish and the cells. And because we start at 0 here, even though we've only got 20% left at this far end, that is still a concentration gradient, so more and more. So at every single point along this gill, there is always a concentration gradient, which means all the oxygen in the water can diffuse into the fish. Rather than, I think in the example that I gave in that video, is sort of there was like an equilibrium about 60%, which meant 6% of the oxygen didn't get to the fish. The question I had, this is actually really clever. What about carbon dioxide? Because of course, carbon dioxide must be exchanging at the same time. Now the answer, and this sounds simple, but the answer is exactly the same. The carbon dioxide is also on a counter-current system, but you kind of have to see it. So in this case, if this is all now about carbon dioxide, again, I've got water going one way, blood going the other, counter-current system. So now, well, the blood, because it's just been to all the cells, it will have as much CO2 as that fish can possibly produce from respiration, 100%. The water coming in hasn't yet been around a fish, so when it comes to carbon dioxide levels, it's going to be as low as it possibly will ever be. So I'm just doing exactly the same as the example for oxygen. It's just the blood and water arrows are the other way around. So I'm definitely going to get diffusion here. And I'm definitely going to get diffusion here because this is 0 and this is 100. And it ends up with a system, again, it's as if I've just swapped it round, isn't it? Where more and at every single point, CO2 can diffuse from the blood into the water. Counter-current system, not just oxygen, it's oxygen and CO2. Okay, I've got one final question to have a little mini discussion about. And this is, again, this is my favourite question I'm really proud of the person who asked this. They are clearly thinking at a really high level. So one of the more difficult things to do with insects is the idea of the tracheal fluid and it withdrawing. Now, I didn't really get any questions about why that happened. I think people were relatively okay that it increases the surface area available. So more oxygen can, and therefore more CO2, can diffuse from cells into the tracheoles. There's more space there, so there's more diffusion between the tracheoles across their very thin walls compared to if the tracheal fluid is all the way up. The question I was asked was, why is the tracheal fluid there to begin with? And there's no massive reason why is there tracheal fluid. It is just there. We'll learn in a future topic about how we form something called tissue fluid. Tissue fluid is a type of fluid that surrounds all living cells. That's all tracheal fluid is. It is just the fluid that naturally surrounds all its cells. But some of that fluid can seep up into the tracheoles because they've got an open end. They're not. It kind of looks like they're closed here, but they're not. It's completely open at the end to the tissues, to that tissue fluid. And at rest, some of that tissue fluid just seeps upwards into the tracheoles, and we call it tracheal fluid. But why is it really important? Yes, we talked about having a larger surface area, but also at rest, if all that tissue fluid seeps upwards, well, of course, all this fluid here is going to have a lot more oxygen in than sort of the surrounding tissues here and here. It's going to have loads of oxygen in this fluid here because it's right by the air. It's right by the airways, right by the tracheoles and the air that's going in. How most insects suddenly withdraw the tracheal fluid, it can be as simple as a movement of a single muscle, like a wing. That movement of single muscle will just kind of squeeze the tracheole slightly, and it forces all that tracheal fluid this way to where all the... This is embarrassing. I'm trying to write with the... Yeah, I think that says cells. I'm going to take that. It forces all the tracheal fluid this way towards the cells. Tracheal fluid that has just been in contact with loads of oxygen. Highly oxygenated tracheal fluid with one little wing movement is now surrounding their cells. Their cells which desperately need the oxygen to respire, to produce ATP, to keep up with muscle contractions. So thank you for that question. Thank you for all the questions. And to the 8 of you who didn't reply, you are now black marked. And I will be contacting you separately. And if I don't hear anything, I generally will be ringing home. Mainly I'm just be worried about you. I'm already not sleeping. So if I'm worrying about that as well, I definitely won't sleep. So thank you very much. Expect more correspondence from me very soon regarding plant transport and the next topics. Yeah, I'm going to try and close this. Discard. Right, peace out everyone. Bye-bye.